Hi everyone, my name is Ryu and I am a graduate student from University of Illinois, Urbana-Champaign. And today I would like to give you a talk about our latest work, Biscatter, which is the integrated radar two-way backscatter communication and sensing with the low-power IoT tags. This is a joint work with Luke Jacobs and Professor Elahi, also from University of Illinois, and Jinhua Wan and Professor Stephen Bowers from University of Virginia. So to begin with, I would like to first give a little introduction about the general radars. So, radars has been known as a strong sensing device that is widely adopted in many applications such as cruise control systems on automotive vehicles. Radars are known to have such a huge advantages over other sensing devices as it can operate in any weather or lighting conditions, and it can penetrate through the objects and the obstacles, and it is also capable of sensing the environment at the low power. But today, radars are not only limited to the cars. For example, they are embedded in robots in the factories for object detections, and in smart warehouses, it is equipped in the drones to do the environmental sensing and obstacle avoidance, and even in phones, like in Pixels, it is used for gesture and posture recognitions. So now, with the radar being such a powerful sensing device, the question is if we can elaborate the radars to use it for communications as well. That leads us to radar backscatter communication, which can enable a communication on top of the radars with a low power backscatter tag. So in the backscatter communication, the radar will transmit some carrier wave signal, and on the other side, we have a backscatter tag that can operate in two different modes, which is on and off modes. So when the tag is on, it will reflect the signal transmitted by the radar directly back towards it. And on the other hand, when the tag is off, it will absorb all the signal, which ends up no signal get reflected back to the radar. And usually in backscatter communication, we switch this two modes on and off simultaneously, which will end up reflecting and modulating the signal back towards the radar. And on the radar side, we can use on and off keying to decode the message from the tag. The research community has been investigating a way to integrate this backscatter communication in radar sensing systems, adding the communication feature on top of it. However, this technique will only enable communication from the tag to the radar, while the communication from the radar to the tag is relatively unexplored. So this limits us for having the two-way communication link between the radar and the tag. So establishing an integrated radar two-way communication network can enable many interesting applications. So like in this warehouse settings, for an example, imagine you have a tag inside asset boxes, and you can use the radar equipped on the drone to write the information to the tag. For example, you can mark the asset as a fragile item, and we can also have a tag equipped on the robots, and we can also use the radar equipped on the drone to write the commands to the robots, like telling them what is the next tag to do, and so on. In this work, we present Biscatter, which is the first radar backscatter communication system that allows a simultaneous two-way communication and sensing. So Biscatter has three main features. First, it enables a downlink communication from the radar to the tag on top of the radar waveforms, which will then be at the same time modulated by the tag for the uplink communication from the tag to the radar. And then the radar using the received signal to detect, decode, and localize the tag simultaneously. So first, let's look at the Biscatter's downlink module. To achieve the downlink communication, we had to overcome two major challenges. So first, how can we decode the bits on top of the radar signals without losing its sensing features? And second, even if we can do that, how can we decode that using the low power IoT tag? So let's first look at what does the common radar waveform looks like. In Biscatter, we use the type of radar called frequency modulated continuous wave radar, which is one of the most commonly adopted radar in industries. As the name suggests, the FMCW radar will transmit a waveform with a linearly increasing frequency, which are called chirps. As the signal hits the target object, it will bounce back to the radar, and in this scenario, the reflected signal will experience some delay, which is caused by the time required for the signal to travel through the air. And by mixing this received signal with the transmitted signal itself, the radar will end up getting a constant tone signal called IF signal, where the frequency is equal to the beat frequency between the transmitted and reflected signal. One key observation here is, since the slope of the chirp remains the same, the beat frequency of the IF signal will increase as the range between the radar and the tag increases. Therefore, we have a linear relationship between the frequency of the IF signal and the range between the radar and the tag, and thus we can solve for the range by just measuring the frequency of the IF signals. Then let's come back to our original question. How can we encode different bits on top of the FMCW radar signal without losing its sensing features? To answer that, we look at different parameters of FMCW signal, and the easiest to leverage for modulation is the chirp slope. So we designed the modulation scheme called chirp slope shift keying modulation, where the different chirp slopes carry different symbols. Like here, we have two chirp slopes carrying 0 and 1 bits. But first, let's see how the tag will be able to decode this in the low power fashion. So a naive solution will be just sample the received signal at the tag and just reconstruct the signal and calculate for the slope. However, one big problem here is the required sampling rate. For example, if the radar is operating at 10 or 24 GHz, which are common radar frequencies, based on the Nyquist-Shannon sampling theorem, we need sampling rate twice as much as the frequency where the radar is operating with, which will significantly increase the tag power consumptions. Instead, in Biscatter, we designed a low-power decoder, which brings the signal frequency down to sub-kilohertz level for analysis and decoding. So upon the reception of the signal at the tag will split the received signal into two paths with a slightly different delays and then mix them back together again. After mixing, we will get the tone signal with a constant frequency, where its frequency is proportional to the length of the delay lines and the chirp slope. Have you noticed that you have seen this type of processing before? Yes, we get this intuition from how FMCW radar works. So instead of signal having a delay caused by the time of flight, we manually added the delay using two cables of different length. So technically we have a mini FMCW radar structure decoder inside the tag. One key point is that since we know the amount of delay added to the tag and we know it doesn't change, then we can calculate the chirp slope based on the observed beat frequency after mixing. Therefore, by analyzing the frequency of the IF signal, we can easily decode the bits encoded on the radar's FMCW waveform. So, putting everything together, here is the tag schematic, and it contains the decoder module that we just explained, which is integrated with the uplink module for modulating the radar reflections before sending them out. And here's a ritual effective antenna structure to boost the tag reflections. So to see the entire tag operation, the radar sends a modulated sequence of the chirps. The tag receives the signal and decodes it, and at the same time uses an R switch to modulate and reflections for the uplink. The radar then receives these reflections and searches for the tag modulation to identify and localize it. And here is the sample of tag's reflection received at the radar. So we can see the tag's reflection switching on and off here. So one challenge is that the changing radar chirp slope can cause some ambiguity in the localization estimation of the tag. So we get the tone signal with the constant frequency, where its frequency is proportional to the length of the delay line and the chirp slope. So fortunately, since the radar knows every configuration of the chirp it sends, we can apply a software corrections to the signal we receive to remove the ambiguity. The plot shown here is a corrected version of the signal. So as you see, now we can clearly see where the tag is actually located, and the tag modulation is more obvious. So please refer to our paper for the detailed theory and the math of how this correction are being made. So lastly, we define the packet structure for bit synchronization. The radar packet consists from three main parts, that is header, sync bits, and data payload. The header is a sequence of chirps with a fixed slope that are used for packet detection, and it also defines the mode of communication, and we also use it for estimating the chirp period or the bit size. The header is then followed by two synchronization bits, again with a unique chirp slope. We use these two bits for indicating the start of each chirp and also indicating the start of each data payload. Then we will have the actual data payload. Bit symbols are encoded as a different chirp slope here. We have one chirp slope per symbol, and this means that we can increase the data rate by increasing the bit symbol size. The data rate is thus determined by the chirp period and how many bits is encoded in one symbol. So that is the overall features of the Biscatter system. So we talked about how radar can encode the bits into the chirp slopes and how the tag can decode them by simply using two delay lines and then piggyback its bits on top of the radar reflection for the uplink. For the interest of time, I'm not going to the details of the uplink and localization algorithm, so please refer to our paper for more details. We evaluated our system using off-the-shelf radar and the custom built our tag used off-the-shelf components. We then tested the tag performance in several indoor spaces at different distances to calculate the bit error rate. So we first evaluated our downlink performance by measuring the bit error rate for different symbol sizes and radar bandwidths. We used the fixed cable size and the fixed distance between tag and the radar, and the brown bar plot shown here uses the radar bandwidth of 250 MHz. And we can see that the bit error rate increases for the large bit symbol sizes, which is quite expected because the chirp slope get closer to each other. So we also evaluated this with two more different bandwidth setup, 500 MHz and 1 GHz. And we can see that a larger bandwidth can compensate for the bit error rates, so we can have higher data rate while also maintaining low bit error rate. We also evaluated the BR over different distances as well. So as the plot shows, with 40 kilobit per second data rate, it can operate up to 7 meters with a maximum bit error rate of around 0.1%. We also evaluated this with two other data rates as well, and as we can see, that the fixed distance between the tag and the radar, a slower data rate generally performs better in terms of the BER, which is also quite expected. I should also note here that this is downlink data rate from radar to the tag. While in number it may look too low, but that's more than enough for IoT applications where downlink is usually in the form of sending a command to the tag or just setting up the tag. We then evaluated the Biscatter localization performance, where the radar locates the tag, and we compare it with the baseline backscatter communication, where the radar sends a fixed chirp slope. So we measure the localization performance, and as the plot shows, we get the quite comparable performance between the baseline and our system. It operates well up until 7 meters under the 10 centimeter of localization accuracy. And lastly, we tested the performance of the Biscatter in 24 GHz frequency bands to test the capability of the system to perform in millimeter wave bands as well. So as the plot shows, we get the comparable performance between both the 9 GHz and 24 GHz bandwidths, which shows the Biscatter's performance in operating in higher frequencies. Alright, so here are some takeaway of this presentation. So in this presentation, we presented the Biscatter, which is the first integrated two-way radar backscatter system with low power tags that work with the off-the-shelf radars. And we also proposed a novel chirp slope shift key modulation that used to encode the bit symbol upon the commodity radar waveform, and the low power decoder module to decode that information at the low power IoT tag. And we also evaluated the system, and where the Biscatter achieves 50 kilobit per second with under 1% of bit error rate and operates up until 7 meters of distance. So here are some next steps and future works. So Biscatter opened up new research avenues toward integrated radar sensing and communication, and there are a lot of opportunities for the future works. For example, extending the Biscatter for multi-radar and multi-tag operation, and this follows with the design of a MAC layer protocol on top of the radars, and more importantly, assessing the overall network throughput. And I would like to close the presentation here. Thank you for listening.